Hello, everybody. This is Zach Goldwitzer, and this is the security of enterprise blockchains. So I have not done a whole lot of Bright Talk webinars at this point, so bear with me, but hopefully we will get to all of your questions, everyone that is here on the line, by the end of the presentation. Otherwise, we will have someone from our team actually reach out to you via email. I can be reached at Zach, Z-A-C-H, at chainworks.com. So you can reach out to me, or we also have a general info line, ping, P-I-N-G, at chainworks.com. So if your question doesn't get answered, feel free to reach out on those lines of communication. But anyways, I wanted to kind of introduce myself. As I said, my name is Zach. I am a blockchain engineer at Chainworks, and I've been working on a lot of different protocols. So my aim with this presentation is to actually provide an overview of some of the security considerations of some of these enterprise blockchain tech stacks. I won't be going into really deep levels during this presentation, but hopefully the goal is to get everyone thinking in terms of the different points of vulnerability within their systems, which will spur further questions down the road. So let me get started. I think one of the biggest misconceptions in the blockchain space right now, especially for people who are, generally intelligent and people that are coming in from the enterprise side of things. They've got a lot of experience with, systems that are in place today and are first learning about this blockchain infrastructure stuff. All these kinds of people are very intelligent and can pick up on these things very quickly, but it's still a bit confusing to everyone, the differences between public, private, and consortium blockchains. So I wanted to start out by talking about the differences between these types of blockchains, and also provide a little bit of an analogy for trying to think about them. So I think what I would start with is the internet versus the intranet analogy. So back when all the tech companies were popping up in the late 90s, in the dot-com boom, essentially these large corporations saw all of this happening in the startup world and said, hey, we want to have this too, but we want to control it. And the internet back then was very open, and the communication was not so centralized around the client-server model that we have today. So I think that is a very similar analogy to where we're at with the blockchain ecosystem right now. We have all of these public blockchains that have popped up, like Bitcoin and Ethereum, Quantum, all of these different open chains. And we also have some more private chains, such as multi-chain, Hyperledger, Quorum, Corda, all of these different implementations in the private realm. And a lot of the companies are looking at this and saying, hey, we want to do this as well, but we don't want to expose a lot of our internal information. And so it's helpful to understand the differences between these three types of chains, because I think a lot of times we actually miss the whole point of blockchain altogether. So starting with public blockchains, I think this is the one that most people are familiar with. And this would be, your classic Bitcoin or Ethereum. And they're highly decentralized, or ideally should be. I know there's a lot of argument out there about, whether these public chains are actually decentralized. And they usually have a token that is valued in the market, on exchanges. It's got liquid value. And this actually incentivizes, businesses to spur up mining rigs to actually make money off the network, which then in turn keeps the network secure and keeps it running over a sustained period of time. Now, what we're going to be talking about a little bit in this presentation is more on the side of consortium and private blockchains. So Vitalik Buterin, the founder of Ethereum, he's actually done a good amount of writing on the validity of consortium and private blockchains, because they do actually have a good amount of value if you're using them in the correct way. As you see at the bottom of this slide, a private blockchain is simply a blockchain run on your corporate infrastructure that's not open to any of the outside world. And it's essentially like a database, RDBMS system, except you also have a cryptographic audit trail. So a lot of times, I think people will call this something like triple entry accounting, where you have the debit and the credit plus a transaction receipt, or in other words, the hash of that transaction. So it provides a good immediate value to an enterprise just by that fact. But what we're interested in is consortium blockchains, which kind of mesh the two together. You have a group of companies that will come together and actually run nodes in a known network where everyone is identifiable, but also it's decentralized enough to where you have the data immutability that comes with any public blockchain. And we put on here that it's recommended that you have at least 7 nodes to maintain an acceptable level of security. But that being said, it's very early days of this. This was recommended from Casey Coleman of Monax, which is an ecosystem application platform from Eris Industries. So that's just one take on it. Obviously, I think we'll see how this plays out in the future in more stress testing as actual deployments go live. So here you see a little diagram, and the point of this slide is to actually give an overview of what an enterprise or non-enterprise blockchain technology stack might look like. And it's also to demonstrate that regardless of whether you're on a public permission chain or a private consortium chain, you can actually get the same type of benefits from these blockchain networks. You have the shared infrastructure, which is the chain itself. You have the shared services, which are, I don't want to call them layer 2, but they're essentially protocols built parallel to the blockchains themselves. And then you have security services. So these are all different parts of a blockchain technology stack, but they are relevant to both private and public chains. And the reason that blockchains are so appealing in terms of security is because unlike traditional IT infrastructure, there's actually a good amount of security built into the blockchain itself. And you can see on the right that things like cryptographic hashes, private signatures, consensus via various consensus mechanisms, and replicated data across all of the different nodes actually provides an inherent amount of security already. And so you can see on the left there's a good amount of security properties that we've put together for you to look at. I'm not going to go through all of them for the sake of time though. So before we get into an example of a private blockchain infrastructure and some of the security considerations around that, I wanted to set the stage by presenting, why is a public blockchain so secure, and why were people so excited about it in the first place? And it all kind of revolves around aligning incentives. So, of course, in any organization, the key to doing anything, management, what have you, is aligning incentives so that people are, they don't do things because they've been kindly asked to do something. They do things because they are inherently incentivized to do that, whether it be out of fear or out of monetary incentive like we have with the public blockchains. So a public blockchain like Bitcoin is secure because, one, it has a decentralized network. This is the whole classic 51% attack prevention. And we've actually seen several attacks on the Bitcoin network already although they're not so apparent if you're not looking closely. So I'll talk about that in a couple slides, but that's one of the main appeals to one of these public networks. Also, there's deterministic hashing, which was a property I mentioned on the last slide. Basically, it's the root of the entire blockchain network is being able to take a piece of data, whether it be 2 words or 50,000 lines of words, and you can condense that into a 64-character hash. And that information always condenses into the same exact hash, which provides a tremendous amount of security and verifiability inside the networks. And then finally, you have the consensus mechanism. I'm not trying to go into how a public blockchain works during this presentation, but at least understand the proof of work that goes on in the Bitcoin network. And it has to do a lot with the incentives that I'm talking about, because the miners in the network, they're not doing it out of their own goodwill. They're doing it because they're incentivized by monetary rewards. And they're actually disincentivized to act poorly in the network. And this touches on the concept of game theory in the classic prisoner's dilemma. So let me just paint a picture for you if you're not familiar with this prisoner's dilemma. So essentially, there's 2 criminals, Alice and Bob, and these 2 criminals are convicted of a crime, but the prosecutors don't have any verifiable evidence to actually convict them. So they're both offered a plea, and mind you, they're in different rooms, they can't talk to each other and have no ways of communicating. So they're both offered, a bribe or a plea or whatever you want to call it, that says, hey, both of you, if you want to, you can actually betray your, fellow prisoner, and you'll actually get a better payout because of that. And this is a really important game to look at, because it actually highlights why 2 completely rational individuals might not cooperate, even if it appears that it is in their best interest to do so. And you can see in this diagram here, the best payout to both of them is actually both of them staying silent. But unfortunately, the Nash Equilibrium, or in other words, what is your best option given the other player's actions, will actually lead to both of them betraying each other and getting worse sentences for themselves. So it's these kind of incentives that actually secure a public blockchain in the first place, especially around mining. So you might say, wouldn't the Nash Equilibrium actually favor cheating in a mining scenario? In many cases, there's been, hackers that will go out and try to mine their own chain, or in the classic example of sending Bitcoin to yourself. So they'll send a Bitcoin transaction to themselves, or they'll send it to someone else, they'll revoke it on a different chain, and then essentially mine on that other chain in hopes of retrieving the funds that they already sent. So this would be, total corruption. It would be the double spend problem that Bitcoin aims to solve. And the reason that it is solved is because of the coordination problem in game theory. So right now we have a Bitcoin network that is fully agreed upon to be the main network. And so essentially all of the people on the network are incentivized to stay on that one. So we're actually in an equilibrium up on the main chain, and the coordination problem just describes that in order for one attacker to gain any sort of benefit from mining on a different chain is if they convinced over 50% of the network to actually switch to that new equilibrium. So despite the current state being less lucrative for the attacker and for everyone on it, it doesn't justify actually switching. And that is also supplemented with by the protocol itself, because miners, the software built into a mining node will actually reject blocks, transactions, and all of these pieces of data if they don't match certain syntactical requirements. So not only are the human side of things incentivized to mine on the main chain, but also the computers that are running all day, every day, they'll actually make sure that they're mining the correct chain because they won't make any money otherwise. So finally, I wanted to just touch on why people are so hyped up on this whole proof of stake blockchain. And it also touches on the game theory within, or the incentive mechanisms within the public blockchains. And I know Vitalik has talked a lot about this, especially with his Casper protocol for Ethereum. They're trying to maybe switch over to proof of stake sometime, which would, supposedly save tons of money and save the planet with, you're not expending so much electricity, which is coming from fossil fuels, which is destroying the planet, so on and so forth. Additionally, it is supposedly a better incentive system where you actually introduce the idea of punishment. So you can see in the top diagram here, without punishment, there's actually an incentive to act maliciously in a Bitcoin network. Now, we talked about the coordination problem and why this doesn't necessarily ever happen, but nevertheless, people are actually incentivized to steal, Bitcoin. Now, on the bottom, you can see if you add in a proof of stake system, you all of a sudden add this idea of punishment. So with this punishment, the Nash Equilibrium actually switches over to all the participants in the network acting in good nature. So that's really the appeal to the proof of stake consensus mechanism. But I don't want to spend the whole presentation on this idea of public blockchains because everyone came here to understand what is going on the private side of things. And we've listed out a short list of some of the advantages of private and consortium blockchains over the public ones. Some of them being you have enhanced privacy. Your transaction costs are way lower because you don't have to actually pay transaction fees to incentivize the miners to add your transaction to their blocks. You also have higher transaction throughput as a result of this because you're not having to do this whole elaborate proof of work consensus mechanism. Also, one of the biggest appeals is some of these private blockchains, especially like the one that we'll talk about here in a few slides, is that they have a modular design with pluggable architectures. Or in other words, you can piece together your IT stack around these private blockchains rather than, with Bitcoin, you have to download Bitcoin Core or one of the other popular implementations, and there's not a whole lot that you can do to customize to your needs. And then finally, there's an increased control of the network by the selected administrators. So if you are in a consortium network where, say company A is the admin that takes care of most of the governance in that network, you actually have a much better line of control because, especially with these public blockchains, a lot of people have started to see that making decisions in a decentralized manner is very difficult and does not prove to be a very efficient way to add new features to this. So those are some of the advantages. And I wanted to basically talk about the same thing that we were just talking about on the public chains, but on the private. So going back to the whole 51% attack problem, with private blockchains, it's not so much of a problem because since all the nodes in the private network are supposed to be known, this puts almost an identity to them, and it holds them accountable to act in their best interest. So, say company A, say there's a consortium network of 10 companies, and company 1 in that network decides, hey, I want to rebel and try to get the other, 4 more companies to rebel as well. Now, this has not yet played out in a real world scenario due to the lack of live deployments, but I think eventually we'll see something where, maybe some of the companies are trying to manipulate a network in their own way, but with the press covering companies, every day, it seems to me like there would be a high amount of political instability with that kind of approach. So that's one thing. Also, many of the IT security measures that your company goes through already can be applied directly to these private blockchains. So you don't necessarily need to learn an entirely new technology in order to gain a benefit from the private blockchains. And then finally, these private blockchains come to finality a lot quicker than public, mainly because they're not required to go through these elaborate proof of work consensus mechanisms where it takes between a minute and 10 minutes to actually approve a transaction. So the finality is quicker, so we're getting transactions approved a lot faster, and there's also the ability to configure the network so that the protocols are talking at the highest efficiency possible. And I wanted to briefly touch on the consensus mechanisms available in these private and consortium chains, but I don't want to distract as a result of it. There are plenty of different consensus mechanisms, but I think the main takeaway is you pick the consensus mechanism that fits your situation. So each of these mechanisms listed here have their advantages and disadvantages in different realms. So for example, if your company has if you're a payment processor, obviously you're going to want to have a lot of transaction throughput. And therefore, the last mechanism that you're going to look at is one of those top 3 mechanisms. And you might look, more into proof of elapsed time or proof of existence, which handle that kind of throughput a lot better. But in the end, the only reason that you have a consensus mechanism is to come to a consensual agreement on the global state, or essentially what the blockchain actually looks like at any given point in time. So I wanted to actually come up with a basic example, because at Chainworks we've been working extensively in Hyperledger Fabric for a lot of POCs that we've spun out. So I wanted to kind of give a picture to everyone on the call to understand what this might actually look like in real life. Now, going back to that comment I made about you don't have to relearn everything to implement one of these private consortium or private secured networks, this is because of the modular architecture you see here. So, for example, let's say that we have a Hyperledger Fabric network of 2 organizations. We have organization A and B, which all have a set number of peers. So, say these peers, organization A has 3 and B has 2, and all of these peers are running on their own ports or VMs. You then have each organization running their own ordering service, which this is essentially the node in this network that will take care of consensus and will run the consensus mechanism. And then you also have a global state database. The one that we use with Hyperledger, the one that's currently compatible, is CouchDB. And then finally, you have a membership service provider, typically in the form of a certificate authority. And say organization A might use DigiCert, while B might use VeriSign. So you can see right there that it's a very pluggable architecture. You don't all have to run the same pieces of technology. All that matters is that the state of the network, you can come to an agreement on the state of the network at any point in time. And that all has to do with what chain code you've downloaded to each peer and make sure that the ordering service has been configured correctly for your network. And this also, I wanted to talk about some of the critical operations that you might consider when spinning up one of these networks. And that would be the generation of certificates, which would happen through the certificate authority, whether you're using, VeriSign or what have you, and then the issuance of certificates. So if you remember back to one of the first slides, we talked about how you must keep your private certificates or private keys very secure on your systems. And so this is one of the most major vulnerabilities within the private realm of blockchains, as is for a public blockchain as well. But obviously for a private enterprise blockchain, the individual employees of the company are not going to be held responsible for maintaining their own private keys or certificates. Otherwise, it would be a complete mess. So this needs to be built into the architecture itself, a good management system for these certificates, which, mind you, are stored on each peer that is being run. And not even each peer, but each client. So if you have a client application running in, maybe a back office of a company, you just have a laptop that's making state changes to this network. You actually have to secure those certificates as well. So that would be the most pressing problem with this kind of, not necessarily problem, but security concern in the private realm. But also, there is consideration around each of the state mutations that happens in the network. So that would consist of anything from the creation of channels, deployment of channels, deployment of chain code. When you actually initialize the chain code, that's a big one, because the chain code is essentially the business logic behind the network, and all of the peers in the network have to run the same exact chain code in order for consensus to happen. So there needs to be a policy set by the network administrators to say, hey, organization A, B, C, and D all must approve this chain code before it can be initialized. So there's a little bit of governance in there, as well as security implications. And then finally, actually interacting with the network. Obviously, you need to secure what your employees are doing. So generally, the admin of the network is going to be doing all the configuration stuff, but then the employees that will actually be running transactions or invocations of the chain code, they'll be just sitting at their normal desk, and you need to make sure that those transactions are being sent out on a network securely. So this, in terms of Hyperledger Fabric, everything's running in Docker containers. So it's very important that you provision the virtual Docker network so that you're not exposing ports unnecessarily to the outside world. And you can actually create a virtual network that is completely closed off from the outside world, except for key operations. So that's basically the overview of like a real-world Hyperledger Fabric implementation. I see that I'm running short on time here, so I'll just skip over this a little bit, and just wanted to say thank you so much for coming out today. And feel free to ask any questions. Once again, ping@chainworks.com, P-I-N-G, or you can reach out directly to me, Zach, Z-A-C-H, @chainworks.com. And we'd be glad to answer any of your questions, maybe keep the conversation going. And lastly, just wanted to invite you to our next Bright Talk, which will be, I think, in about a month's time, which we'll be talking deeper on the Hyperledger Fabric architecture.